So in order to do such off-policy learning, we will learn a trick called importance sampling that allows us to do that. But before doing so, we will need to define some probabilities, specifically probabilities of sampling trajectories under the different policies, B and pi. B would be our behavioral policy, pi would be our target policy, the one that we're trying to learn the Q values for. So first we're going to define the probabilities of sampling a specific trajectory from each one of these, and then we'll see how we can use these probabilities to define an importance sampling ratio, and how we can use that to do an unbiased estimation of the Q value for our target policy. So let's start by defining these probabilities. So an agent following some behavioral policy B might sample the following trajectory, right? From S0, it will take action A0, observe an immediate reward of R1, reach to state S1, and so forth until the end of the episode at ST. And now we would like to answer the question, what is the probability of sampling this specific trajectory? So that shouldn't be a problem, right? We've learned about the MDP factorization and the definition of a soft policy. So we can say that the probability of sampling this specific trajectory following the behavioral policy B would be the probability that under soft policy B we will sample action A0 at S0, and then we multiply that by the probability that we will get to state S1 after being at state S0 and taking action A0. So these two probabilities, multiplying them, will define the probability of our first transition, right? Transition at time step 0. Then we multiply that by the probability of the second transition, so the probability of taking action A1 at state S1, and then the probability that we arrive at S2 after being at S1 and taking A1, and so on, right? Eventually, we simply factor all of the transition probabilities from time step 0 until the end of the episode here. Okay? Yeah.
So here the policy B is the same as the probability distribution. We can say that. So B is a policy, right? But we can also, it gives a probability distribution here, because now we have P for probability, and then we also have B as a policy. So does this represent?
B is a soft policy, right? We defined that. Mm-hmm. A soft policy meaning that it provides us with a distribution over the actions. It doesn't tell us for a specific state you always take in a deterministic way a specific action, but it has a distribution over the actions to take. And we actually have to use a soft policy in order to guarantee coverage, right? For a deterministic policy, yeah, with some caveats.
Okay, so B here would be a soft policy.
B here must be a soft policy, right? So if you remember, we defined a soft policy exactly this way. As a probability, it returns a probability for taking a specific action given a specific state. Yes, so B is a soft policy. Same goes for our target policy. Yes, you might claim, and this is fine, that a hard policy is just one version of a soft policy with a probability 1 for one of the actions and 0 for the others. This is true. So conceptually, you could use a hard policy here. However, that might violate the condition of coverage. In some cases, it might be okay, but in many cases, it might violate it. Okay? So normally, we would say you have to inject some exploration. And I don't want to go into there are some caveats, but it will only confuse the audience at this point. Okay, so now let's say that we are able to compute the probability of sampling a specific trajectory. If we have the opportunity, or we are able, the ability to compute these probabilities, can we do a better job in updating the Q values? I'm not talking about Q values for some target policy. If we would like to just compute Q values for the behavioral policy, can we make use of this of the trajectory probability in order to update these Q values?
I don't think we need the probability, do we?
We don't need it, but we can actually use it, right? If we follow the definition of an expected value, right, as a summation of each possible outcome multiplied by the probability of that outcome, we can actually use that and not take a simple average of the returns, but take a weighted average of the returns. And that will actually be much better with respect to the variance. It will help us. So if previously we saw some extreme value, extreme Q value, after taking a very unlikely trajectory, if we take a simple average as our Q values, it will be very noisy. Well, it will push our Q value in the wrong direction. However, if we know that the trajectory came from a low probability, or on the other hand came from a high probability, then we can use that in order to reduce our noise, reduce our variance over our sample. So this can be helpful if we were able to compute these probabilities. It can also be very useful in smoothing out or making our Q estimations less noisy, specifically in highly stochastic environment, very noisy environment. So computing the weighted average based on the sample probability will reduce variance because it will help us eliminate the impact or reduce the impact of noisy sampling. But you might say at this point, and later on we will tie it back to off-policy learning. But for now, just bear with me on learning Q values for our behavior policy. But the problem with the solution that I just gave you, that is to take a weighted average of the returns, is that, well, we cannot practically compute the trajectory probability because we assume that the model is unknown, right? So we can't compute these transition probabilities, these here, right? All of these transition probabilities between each state to the next state. By the way, if we would know these probabilities, let's say you have a domain where you actually assume to know these probabilities, well, then I would say you don't need reinforcement learning, right? You can use dynamic programming, as we saw previously, solve your problem offline, find your optimal policy offline. Okay, that seemed a bit pointless, right? I told you, we have a closed form expression for the trajectory probability. It would be helpful for us to compute this probability, but we cannot compute that probability. Okay? So now I can ask you a different question. Can we say something about the probability of sampling a specific trajectory for a policy, a target policy that is different from our behavioral policy? So this is an interesting question, and actually the answer is pretty straightforward, right? Yeah, sure, we can do the same computation. We can define, maybe not compute, but we can define, following a very similar definition as we saw for the behavioral policy. We can also define the probability for a specific trajectory, for sampling a specific trajectory, for any policy other than the behavioral policy, right? It would simply be to replace the B here with some target policy, which we assume to know, right? We know the policy, our target policy, we know our behavioral policy. We assume to know them. Both of them are soft policy in the general case. So again, we can also define this probability for some target policy, but we don't assume to be able to compute it. Okay, what we hope to be able to compute is what's called the importance sampling ratio. So I'm not able to compute the probabilities, but I would like to compute the difference in the probability, the ratio between the probabilities, between the probability of sampling a given trajectory, the trajectory that I just sampled, between sampling that trajectory with my target policy versus my behavioral policy. How can we compute this importance sampling ratio, denoted ρ, without a model? Okay, so again, we cannot assume to know the model. We're doing a reinforcement learning, right? So we can do that because we can eliminate all of the probabilities, the transition probabilities, right? So I wrote out the definition of the probability for sampling a trajectory given, well, either the target policy or our behavioral policy, right, as we defined it in the previous slide. And now you can see that the transition probabilities, well, they are the same in both the numerator and the denominator. So these can be ignored, at least for computing the importance sampling ratio. And, well, we assume to know our target policy and behavioral policy, so practically, even without assuming to know the model, we can compute the ratio between the probability of sampling a trajectory between the target policy and the behavioral. Okay? So we do assume to be able to compute this difference. How can this computation help us? So this is exactly where the importance sampling comes into play. We will use the importance sampling ratio in order to define an unbiased off-policy learning approach. So let's see how we can use that. So by definition, the state value under some policy B for any state is the expected returns after starting at that specific state and then sampling a trajectory from the policy that we would like to evaluate, right? Policy B. Importance sampling will allow us to compute an unbiased estimation of V pi s, so for some other policy, target policy pi, by running our behavioral policy B. So that's our goal. So my claim, or where I'd like to eventually go to, I'll prove it, is that the state value under a different policy pi, not the one that we use in order to sample trajectories, is the expected return multiplied by the importance sampling ratio. I'll tell you, if you have the expected or some GT, some returns from the behavioral policy, that's fine. If you multiply each one of these by the importance sampling ratio for that specific trajectory, you'll be fine. You have an unbiased estimation of V pi s, even though you didn't follow pi. Okay, so in this sense, we set V pi s to be a weighted average of observed returns that are weighted by the importance sampling ratio. And again, these are observed returns after following a behavioral policy B. If we assume that we visit state S over several episodes, m different episodes, and in each one of these policies, in each one of these episodes, we use a behavioral policy B, then we can set V pi s as simply the average weighted, importance sampling weighted returns. And this is what we do in any importance sampling algorithm. Okay, so let's prove that indeed what I said here, that the V pi of s equals the expected returns under a different policy weighted by the importance sampling ratio. A question? Yeah.
Yes, it's a simple question. It's just, so is it called importance sampling because it weighs how important another policy is with respect to your policy?
Right. So the importance here is that you sample some trajectory with a return, with G values, but you would like to know, or you'd like to assign some weight telling you how much is this sample trajectory important for your target policy, right? Okay, so now let's prove that important sampling, or using important sampling, that is weighing the observed returns under a behavioral policy with the important sampling ratio, is indeed an unbiased estimation for the target, some target policy. Okay, so I'll do the proof in a more general sense, right? For any random variables, because you can consider our trajectory is just a random variable, a very complex one, but eventually it's just a random variable. So we would like to estimate an expected value to x, where x is v pi of s, right? This is what we would like to estimate. By definition, the expected value of some random variable x is the summation over all possible outcomes of x of the probability of observing that outcome multiplied by that outcome. And this is true for the discrete random variable. Of course, for the continuous case, we replace this sum with an integral. Okay, now for the case that we don't know the probability for each outcome x, we saw that we can define the expected value, we defined this before, that we can define the expected value over x as simply a weighted, not a weighted average, but an average of all possible outcomes when you sample enough sample, right? At infinity it will be the same, but even for any value, even for a single sample, it is an unbiased estimation. Okay? So this is an unbiased estimation because the samples are coming from the same distribution that defines the probability of any outcome for x. Okay, but now the interesting question would be, what if our samples come from a different distribution, right? A distribution y.